Hello students, this is Mr. Allen. Today we are going to look at natural log integration, section 4.6. I believe this will be, I think this is the last section that we'll cover in chapter 4. Objectives today are two. We are going to use the log rule for integration to integrate rational functions. And we're going to integrate some trigonometric functions, some of the more uncommon ones, and I'm only going to do really one example. You can look the others up in the reference guide. So what is our log rule for integration? We have studied two differentiation rules for logarithms. The differentiation rule for the ln of x is 1 over x, and it's produces the log rule for integration. The differentiation rule dx of ln of u is u prime divided by u, which produces the log integration rule 1 over u du equals the ln of absolute value of u plus c. You're familiar with both of these rules. So let's put those to use in this example. So let's say I want to integrate 1 over 2x. So what I'm going to do here is I'm going to say, oops, I got to turn my pin on, sorry. Let's get the pin going here. So I'm going to let u equal to x. So then du would be equal to, well, that'd be 2 dx, but there's no extra 2 over here. So I'm going to write this as 1/2 du equals dx. So this integral will now be transformed into the following integral, 1/2 integral 1 over u du. So let's go ahead and do the log rule that we saw in the last slide. So this is going to be the natural log of the absolute value of u plus c. And finally, we need to substitute back what u was, which is 2x. So our final answer here is 1/2 natural log of absolute value of 2x plus c. I guess we could simplify this if we wanted to. We could say that this is the natural log square root of 2x plus c as well, using our rules for logs. Let's use the log rule here to find the area with the log rule. So I've given you a graph of a function down here in red, and that function is x over x squared plus 1 equals y. And I want to find the area under that curve above the x-axis and the line x equals 3. So the line x equals 3 would be this vertical line here. So the area that we're looking for is all of this. So where are we starting? Well, we are starting at 0, and we're going to go to 3. So we need to keep that in mind. So our integral will be, so the area will be found by integrating from 0 to 3 our function dx. So that's what we're going to do, and as you can see here, we're going to need to do some u sub again. So we'll let u equal x squared plus 1. Du was going to be 2x. Again, there's not a 2, so I'm just going to go ahead and kind of skip a step here, and I'm just going to call this 1/2 du equals x dx. I'm also going to use our change of variable formula that we talked about earlier in the chapter. 0, that lower limit of 0, is going to change to 0 squared plus 1, which is 1. And that's based on this formula here. We're changing the variable from x to u. So then we got to do the same thing with the upper limit of integration. So 3 is going to change to 3 squared plus 1, which turns out to be 10. So to do our integral now, we're going to convert it completely. So we're going to use this, we're going to use these, and then we're going to do our substitutions. So it's going to be 1/2 integral from 1 to 10 of 1 over u du. Well, we can go ahead and do the antiderivative of that, which is going to be the natural log of u, and we're going to evaluate that from 1 to 10. which is going to give, and notice I didn't do absolute value here because they're both positive. So that's going to give us, after a little bit of simplification, that's going to give us the natural log of the square root of 10. That's my final answer. That's the exact answer. If you want the approximate value there, and you can verify this, it's 1.517. Okay, so that's the approximate value, the approximate area under that curve. So again, we found this area here. Please note that this only goes up to 0.5, so that's why that answer is not, something bigger than 1.5. Okay, let's do an example 3 of polynomial long division. So I'm trying to evaluate this, and you might want to try U sub, and you're going to find out it doesn't really help you too much. So what we're going to do is we're going to do some long division. So we're going to do x squared plus 1. That's our divisor. And we're going to divide that into our numerator, which is x squared plus x plus 1. And let's see here. X squared only goes into x one time, so that gives us x squared plus 1. And then when you subtract this, you're going to be left with, well, just that x is going to come down. Everything else is going to cancel. So there's your remainder. So I claim that x squared plus x plus 1 over x squared plus 1 is equivalent to 1 plus x over x squared plus 1. And of course, now we are integrating that. So I'm just actually going to kind of speed this up here. I'm going to integrate this. What is the antiderivative of 1? Really, that's x. And now we've got this x over x squared plus 1, which we actually already did that in example number 2, which was our last example. So it turns out that the antiderivative for that one is going to be plus and then 1/2 the natural log of absolute value of x squared plus 1, plus c. Again, we could simplify this further and say it's x plus the natural log square root of x squared plus 1 plus c. So that would be the solution for that. Okay, by the way, this answer is fine as well. This answer is okay too. I like to use my log rules. Okay. So here are our basic rules for log integration. I've already done 3 examples. Basically, you need to learn that list of integration formulas, and you got to do your U sub and all that good stuff. And of course, if you have access to a computer software or graphing calculator, you can actually use that to see if you get the right answer. Wolfram alpha, for example, is a good example. All right, so now let's look at a differential equation. Now we're kind of getting ahead of ourselves. Chapter 5 is actually differential equations, but that's okay. So this is a differential equation because it's got an equal sign. That's what makes it an equation. It also has a derivative, so that's what makes it a differential equation. So the first thing we're going to do here is we are going to separate the variables. So we want all the x's on one side and all the y's on the other. So in this particular example, I'm just going to write that dy is equal to 1 over x ln of x dx. The only thing I did is I multiplied that dx to the other side. Now I can integrate both sides, and I'm going to get y plus c equals, now this side over here is going to require a little bit of effort. So I'm going to do a u substitution of, let's do the ln of x, which is right here. And then if u is the ln of x, then du would be 1 over x dx, which is beautiful because that's the other part of the integral. So now I'm basically going to integrate 1 over u du. So after a little bit of work here, I've got y plus c. I integrate, I get the natural log of the absolute value of u plus c. I need to substitute the ln of x back in, so I get y plus c equals the natural log of the absolute value of the natural log of x. That's kind of interesting, plus c. And of course, I can add, now be careful. This technically, I guess I'm not quite right here. This would be like c1. This would be c2. C1 and then C2. So what happens when you subtract C2 from C1? Well, you get C3 or something like that. I'm just going to call it C. So this is going to be my final answer. The natural log of the absolute value of the natural log of x plus C. That's my final answer. So that's the solution, and it's a family of curves, and there's infinitely many of them. That's why that plus C is there. Any curve of that form, whatever C you want to use, is the solution for that differential equation. Here are some of the trig integrals. I'm not going to go through these. Of course, there's the basic ones here at the top, and then they get a little bit more complicated as you go down. I'm actually going to kind of derive one of these. And actually, I should have changed that. I'm going to do that in this. It's not example 3. It's this example here, example 5. So it says find the average value of f on this interval. Okay, so the first thing we need to be aware of is what is the average value of a function. So the average value of a function, the formula is 1 over b minus a. This is from a previous lesson. Integral from 1 to b of whatever f of x is dx. So in this case here, we know that a is 0, b is pi over 4, and then of course f of x is our tangent x. So that's what we're going to need to do. So I'll just call it AV is equal to 1 over pi over 4 minus 0 integral from 0 to pi over 4 of, that's pi over 4. Sorry, that's horrible looking. That's pi over 4 of tangent x dx. Okay? So let's focus now just for a second, if you will. I'm going to kind of do it down here in the bottom. What is the integral of tangent x? Now, it's on that previous slide, but I want to show you the derivation of it. So what is this? Well, we know that tangent x is the same thing as sine x over cosine x, right? So if I were to integrate that, if I was to integrate this guy, you would do a u sub where you would let u be cosine. Now, when you do the derivative of cosine, you get negative sign, and you'll notice there's no negative. So my hope is it should hopefully make sense that this is going to be negative the natural log of cosine of x. And then, it'd be plus c. But that's what that integral would be. So we're going to use that now in this problem. Now, I'm going to go back up to here. Now, keep in mind, this 1 over pi over 4 minus 0, that's just going to be 4 over pi. And then the antiderivative of tangent x is this thing that we just got. So I'm going to put this negative out here in front. So there's this negative, okay, it's negative if I put a purple color there, times, and then it's going to be the natural log of the cosine of x. And we need to evaluate that from 0 to pi over 4. And I'm going to actually kind of stop here because I'm going to run out of room. And I'm going to tell you that the final answer here is going to be, and I apologize that I'm squeezing it in, it's going to be negative 4 over pi natural log of radical 2 over 2. That's the answer exactly. And of course, if you wanted the decimal of that, if you're using your calculator and you want to check, it's going to be roughly 0.441. All right, let's call it a day.